In the last sections, we learned how to graph higher degree polynomials, or how to come up with an equation given a graph. What we found was that the factored form was the best to work with when we were going from graphs to equations, equations to graphs. So how do we get these higher degree polynomials into factored form? That is the question. 2.3 is going to be dealing with that. We're going to be looking at long division and synthetic division, and these division processes are going to allow us to write these into factored form. So here's a quick analogy. If you had 4 times x and you were trying to figure out what are the factors of 8, and you knew that 4 was one of them, well, to find the other one, we would simply divide. So what you would get is that x equals, and then 8 over 4. So long division, long ago we learned we would set this up in a box, and then we would divide by asking how many times does 4 go into 8? Well, 2. So what I want you to notice is that 2 times 4 are the factors that make up this 8. So 2 times 4 equals 8. Well, same thing with these higher degree polynomials. If you had x minus 2 as a known factor, and you wanted to break this down even further, so this cubic down even further, we would also do division. What we would find then is this question mark would be equal, or the result of dividing these two polynomials by each other. So if only we could go ahead and learn then how do we accomplish this task. Because in that case we would find out, well, whatever this is times this, it would equal that. So that is where we're headed. Okay, so sorry, for now you will be given a higher degree polynomial and a root or solution, or maybe many roots and solutions. But what we're going to be doing then is breaking those higher degree polynomials with division down. So we will reduce those higher degree polynomials into manageable quadratics, because we know how to manage quadratics, the quadratic formula or factoring quadratics. So go ahead and write these steps down. There are 3 major steps that we're going to use in order to complete this long division process. And we're just going to basically be repeating these 3 things over and over again. Another thing to remember is when we're setting up a division box, what I'm going to ask you to do is make sure that you have an exponent represented for each column in the division box. If an exponent is missing, we need to use a 0 placeholder. Right? And then also keep columns restricted to like terms. What I mean by these 2 slides I will show you in this example. Alright, so we're facing this problem again. So first of all, what I would like to show you is that this unknown polynomial is going to be the result of taking x to the third minus 7x plus 6 all over x minus 2. Just a reminder, the top number is what we call the dividend. Dividend, I'm going to run out of room. Dividend, and then the bottom number is the divisor. Alright, I like to say top dog in the house. So I'm going to set up my box, and that top number, or the dividend, is what goes underneath that dividing box. So here's where I'm going to use that previous slide's tip, that we want to represent in each column a degree. So if we were missing, and for in this example we're missing the degree 2 exponent, so what we're going to want to do is we're going to want to put a 0 placeholder in there. So I'm going to put a plus 0 x squared in there, and then we can go on and carry on with the polynomial. Because here we have a degree 3, degree 2, degree 1, and then x to the 0, which we never write. Alright, and then on the outside we have our divisor. So I'm going to go ahead and start with this factors job, or this first step, and I'm going to ask how many times does the first term in the divisor go into the first term of the dividend. So if you need to, we're going to ask ourselves, well, x times what is equal to x to the third? So I'm just going to divide those. And what I will get is just x squared. So I'll put that in the proper column, and that was the first job completed. Alright, next step then is the checkers job. What we're going to do is we're going to check the work of the factor, and so we're going to take whatever they got, and we're going to multiply it by the whole divisor, so by this x minus 2. So when we do this, we're going to get x squared times x is going to be x cubed minus 2x squared. So here, I'm going to put that down here, and what the checker needs to make sure is to check that these are the same. If they are not, then the factor did something wrong and you'll have to go back to the factors job. So now the subtractor is up, the subtractor and puller downer. So what we're going to do is we're going to subtract these. Now that the checker checks the work, we're going to subtract from these values from the top. That's why it's also important to line up in proper columns, because we won't be able to subtract otherwise because they need to be like terms. So the subtractor's job is very important because this is where most of the mistakes happen. When you subtract everything, you have to keep in mind that it's everything. So this sign, for example, would change. So what I like to do is I like to change that to addition, but then distribute that negative, to everything in here. So that would switch these signs around. So these cancel out, which is what we wanted. As long as the factor and the checker did their work right, that's what should happen. And then these are going to end up being 2x squared. So then I'm going to pull this down, minus 7x. Alright, and then the subtractor's job is done. Now we are back up to step number 1, which is the factor. Alright, so factor again is going to now look at what is this term, how many times does this term go into this new polynomial that we got through this process. So we're going to take 2x squared divided by x this time equals, and then we're going to get 2x. Alright, so therefore I'm going to put positive 2x up here. Now the checker is up. The checker is again going to take that factor's job and multiply by that whole divisor, and then we're going to get 2x to the second minus 4x when we distribute this through. So line that up, 2x squared minus 4x. These checked out, so the checker is done. Subtractor is up again, so what they're going to do is subtract this whole thing, which again we want to make sure I'm going to change that into a plus, but then negate the following signs. So we have, those are 0 because everyone did their job right. We have negative 3x plus 6. Subtractor is done. Oh, sorry, I pulled that down and that's where I got that plus 6. Now we're back up to the factor. Through this work, we're going to ask ourselves x times what equals negative 3x. So in other words, negative 3x divided by x, and we will get negative 3. So I'm going to place negative 3 up at the top. We're going to do the checkers work, which is again taking that factor's job and multiplying by the divisor. And we're going to get negative 3x plus 6. So what happens is these are going to actually just cancel each other out, right? Because they're opposites, so we're going to get remainder 0. What you would do is you would take the remainder and put it over whatever is the divisor is. But since 0 divided by x minus 2, 0 divided by anything is just 0, we don't need a remainder. So what we have found, don't forget, is this times this is equal to our whole dividend. So we just took x squared plus 2x minus 3 and then times x minus 2. And we just established what are the two factors that would equal this whole degree 3 polynomial we knew. Put any remainders over divisors. Alright, here's one last kind of example of the long division process that I did. It's a very long one. Keep in mind what I was doing was this. I did my placeholders because I did not have an x cubed or an x squared, so I had to put zeros for those. So one last thing, if we do have that remainder, what we'll want to do is just put plus and then negative 856 over x plus 3. Now what I want to indicate to you is if we ever have a remainder like this, the idea is that x plus 3 was not actually a factor of this whole degree polynomial. For example, if we had like 9 divided by 4, and we did our long division, 9 over 4, top dog in the house, 4 goes into 9 2 times, and then we would have gotten, well, a remainder 1. We would have 1 and a 4. The idea is that 4 then, therefore, is not a factor of 9. If you get a remainder, they're not truly factors of that whole higher degree polynomial in which you're trying to divide. I'm going to show something that's not a coincidence, but a different kind of method that we could use for this long division. Note that when I do this, you're going to kind of be drawing on what were the main important pieces that really played an effect in this long division process. So what I'm first going to do is I'm going to take whatever I had that I was trying to divide, and I'm going to put that in what we call a synthetic division box. And it's just like a long division box, but upside down. And I'm going to take just the coefficients. So negative 13, I will need those zeros for placeholders. Alright, and then on the outside of this box, instead of putting a factor, what I'm going to do is the roots. So if I set this thing equal to 0 and solved, I would get the root. negative 3. So the very first step that I'm going to do is I'm just going to bring down that first coefficient. I'm going to multiply these, so I'm going to get negative 3, and I will add these, so I'll get negative 16. I'm now going to multiply that result by my root, that negative 3, and I'm going to get 48, and I will add those. Okay, so kind of think about where these are happening. Like, for example, we did add a 0 plus 48 right there. All right, I'm going to multiply these. So kind of think, where did that happen in this whole process? Well, right here. But we're going to get 144. Oh, negative 144, sorry. So I'm going to take that result of adding and multiply here. I'm going to get 432. And then I will add that column. What I will get is 312. I'm going to multiply those, and I'm going to get negative 936. So kind of think, where did that happen in my long division process? And I will add those. I will get negative 856. So what I want you to note is that this was a degree 5 polynomial, but now it's going to be a degree 4 polynomial because I broke it down by 1. This will be x to the third, x to the second, x to the 1, x to the 0, and this will be my remainder. And so if you wrote this out, these are exactly the same. So that is not a coincidence. This shortcut is what we call synthetic division. I'm going to do one more example of synthetic division, and just like we had for long division, that step-by-step process, I would like you to create a step-by-step process for synthetic division. So again, what we are going to be doing to solve for this unknown factor is the division, but instead what we're going to do is the synthetic box that looks like this, and we're just going to place the coefficients in that synthetic box. We still do need, this is x to the third, x to the second, x to the first, and then x to the 0. We still do need placeholders, and if you want to, you can kind of put that there just to remind yourself. And then remainder, x to the 0. Okay, so those are just there to kind of remind ourselves that we needed a placeholder for each one. And then here, though, be very careful. We're going to put the root on the outside of the synthetic box. So knowing that x minus 2 is a factor, we could set that equal to 0. What we would do is solve for it and get 2 as our root. Create your own steps, but what I'm going to do is I'm going to bring down that first coefficient, then multiply that by the 2, by my root. I'm going to add these up together. I'm going to get 2. Multiply that result and put that in the next column. Add those. I'm going to get negative 3. Okay. Multiply those. I'm going to put in the next column, and then I'm going to have 0. Now, what's happening when we divide these higher degree polynomials by degree 1, we've broken it down by a degree 1. So instead of being x to the third still, x to the second, x to the first, x to the 0, this is always going to be our remainder, x to the 0, x to the 1, x to the 2. So you can see we broke this down by 1 degree. So our final answer would be 1x squared plus 2x minus 3 x to the 0, but I'm not going to write that, remainder 0. So we just found the same thing, but with a shortcut method, the synthetic division. All right, how do we use synthetic division? Well, it's a quick way, just like long division, to determine if a value is a 0 or not, or a factor. I should actually 0/factor, because if you know your factors, you know your zeros. But really the factor, if it does not have a remainder, then it is a factor, and therefore you can find zeros. If it does have a remainder, then it's not a factor, and you have not found anything. You can find the factors of the polynomials then. Again, we use synthetic for this. I'm going to just copy the work that I had from the previous slide. So now that I found that these are going to be factors that multiply to be x cubed minus 7x to the 6th, I can see, hey, this quadratic, I know how to factor. So I can just go x plus 3 times x minus 1 times x minus 2, because I broke down quadratics because we know how, and now I have completely factored this. And if I wanted to find all of my x-intercepts, well, just set each one of those factors equal to 0, x equals 1, x equals 2, and what I just found was 3 x-intercepts that would help me graph this thing if I needed. Alright, there's your homework. You're going to use long division and short division, or synthetic, I should have written synthetic division, to complete the problems 5 through 11 odd, and then just follow the instructions to break down completely higher degree polynomials for 49 through 51.